Welcome to the course on design of power electronic converters. We had started discussing with the module gate drivers, and last lecture I had given you an introduction of gate drivers, and I told you what is the need of gate drivers. So, now let us look more into the gate driving circuit requirements. To understand that, let us first look into the turn on and turn off process of MOSFET, and as we had seen before, turn on and turn off process of MOSFETs and IGBTs are similar. So, we can take either of them and understand, and the same applies for IGBT also. So, here there is a MOSFET, and this is the gate circuit. So, this VG actually replaces the driver that you may be using, and so this is represented like a switched voltage source. So, then we have the gate resistor RG, which is connected between your gate and the gate driver circuit. And then we have this diode over here in the power circuit. So, this is part is your power circuit, where we have the DC supply VDC, which forms the DC bus, and then we have a diode, and when we have formed a current source using an inductor. So, you can assume it to be a large inductor. So, what happens is that whenever the switch is turned on, the MOSFET is turned on, then this current flows through this MOSFET, IL current flows through the MOSFET, and when the switch is turned off, so then the current reveals through the diode. And this is the nature of your VG waveform that is supplied by this gate driver circuit, which it is replacing as a voltage source. So, you have this as the DTS as the duty ratio time period, and TS is the switching time period. So, DTS time period, it will be high, that means it is supposed to turn on the MOSFET, and then rest of the time it is low, which is it is going to turn off the MOSFET, and it reaches to this voltage of capital VG. Okay. Now, here for simplicity I have shown these to be just an instantaneous increase and decrease, but in reality it will be not so, and that we will be seeing just in a while. Okay. So, now also recall that your MOSFET, it has these three capacitances associated with it. Parasitic capacitances, one is your gate to drain capacitance, then is your gate to source capacitance, and drain to source capacitance. Further, you have to recall that we had defined this gate to drain, we have renamed it as CRSS, which is your reverse transfer capacitance. Then your CGS, gate to source plus gate to drain, that forms your input capacitance CISS, and your CGD plus CDS, that forms your output capacitance COSS. And these are not some fixed capacitance values, but they actually vary with the drain to source voltage that appears across the MOSFET, and this is what that plot is showing. You can see here that this input capacitance does not vary much with your drain to source voltage as it changes, but your output capacitance that varies to some extent initially for as the drain to source voltage changes, and the CRSS, this you can see it changes a lot with the change in drain to source voltage. Now, these three, as we have seen before also in the last module, they play very important role in the turn on and turn off process of the MOSFET. So, now This is your gate to source voltage VGS, which appears across the MOSFET. Now here what we see is that from this time T0 to T1, for this time period the voltage first increases and it reaches to the threshold voltage VTH, and at that time no change happens. The voltage across the MOSFET does not change, it is VDC, and the current through the MOSFET also does not increase, it is equal to IDS, and we had seen that this is called as, this time period is called as the delay time. Now what we didn't see over there is the gate current. Now what will happen is that during this time period, which is called as your delay time period, during this delay time period, this QGS1, that means this capacitance CGS is going to be charged. So this is the direction of the current over here, this current is going to charge this CGS, alright. So that we can call it as your QGS1 is the charge associated with it, and it reaches to the threshold voltage, and you can see that this gate current is decreasing. Now why we are showing that the gate current is decreasing? Because over here there is no charge initially. So you can say that it was 0 volt was there. So whatever was the Vg that was applied over here, so Vg by Rg is the peak gate current, Ig peak, that we can say is the current that will flow at T0. So this is that current, it flows Vg peak. So this is your Ig peak, from where it starts, and it is going to decrease as this CGS is going to be charged. So it decreases, then it reaches the threshold voltage. Once it reaches the threshold voltage, what will happen is that your current will start to increase, and at that time this diode, the drain to source voltage does not change even then. So this current increases and it reaches to this steady state current, you can say that IL, capital IL, and at that time also it is continuing to charge this CGS. So the charge associated with it is QGS. So this is that QGS1, further it keeps on building up, and this gate current continues to decrease over here, okay, and this gate to source voltage, it keeps on increasing and it reaches to this voltage, which is your VGSPL. We can say that that's your Miller plateau voltage. This is the Miller region. This region is the Miller region. Here what happens, your this voltage becomes, the gate to source voltage becomes constant, it is not increasing. So what happens over here is that this CGD was initially blocking the, or was charged to the voltage of VDS, whatever was the blocking voltage. That means this voltage was, so if your MOSFET was blocking plus minus VDC, as we see here, this is that VDC which it has to block when it is off. So this VDC is what appears across this, is what this CGD was having the initial voltage as. Okay. Now what happens is that as this capacitor starts to discharge from that VDC, that means your current flows through this and it flows in this direction and it discharges this capacitor CGD. Okay. And during that time the charge associated over here is your QG, QGD, okay, and the gate to source voltage does not increase at that time, and the current is almost also you can say that it is kind of constant, and we can call it as your IGPL, and the voltage that decreases during this Miller period. After this, your device is almost on, because your voltage has also reached to almost towards your on state voltage, and current has all previously itself it has reached to the on state current. So, the device is almost on, but what happens is that your here we had applied this voltage capital VG, and so this VGS actually has to reach to this capital VG voltage level, and so this CGS it further charges, this further charges to capital VG, to this voltage level, and that is that you can say that is QGS2, and this voltage gate to source voltage increases further and it reaches to this level of capital VG, and this gate current IG it further decreases and it almost becomes close to 0. So, this is the turn on process. We had looked into it, but now we looked into more from the perspective of charging and discharging of the capacitors. This total charge associated is this your QG charge, okay, and the gate to source charge is the sum of this QGS1 and QGS2. So, QGS, this is equal to QGS1 plus QGS2, and then we have this QG, which is your sum of QGS plus QGD. Now, let us look into the turn off process, which is similar, and it's actually the opposite. So, first this voltage capital VG it decreases, and it decreases to the Miller plateau voltage VGSPL, and at that time the current flows in the opposite direction and it reduces in the opposite direction. So, that means what is happening over here is that now the current is going to flow in this direction opposite while turn off, and it is going to discharge this CGS whatever was the extra charge apart from what was associated with the Miller plateau voltage. Okay. So, that means it is this QGS2 which is going to be taken off first, and at that time nothing happens. This is actually your delay time TD off, and then it reaches to this Miller voltage. Once it reaches to this Miller voltage, at that time the current does not change, the voltage does not change, and this voltage builds up. But however, the current remains same, it does not increase. So, at that time what is happening is that your this current is flowing in this direction, and this plus VDC voltage again starts to build up across the device, and so across CGD. So, it charges to VDC, this capacitor CGD, and the charge associated here is equal to QGD. Then further what happens is that it comes down to the threshold voltage level once the Miller period is over, and during this time the gate current reduces, and at that time your this inductor this drain to source current it comes down to the close to 0 or the leakage current. And further, your MOSFET, in case of MOSFET, it is almost off, the device is almost off once it has reached the threshold voltage, but in case of your IGBT you may be having tail current, and still the turn off may take little longer, this current may be still flowing like this, okay, but in case of MOSFET it will be almost off. So, whatever is the voltage here and the gate associated gate current, so the gate current will continue to decrease and it will almost become close to 0 at the end of this interval, which is your T4 dash. So, what we see from here is that it's your capacitance CGD which plays a very important role, and your capacitance CGS. Your CGS, gate to source capacitance, it is charged during the turn on process and it is discharged during the turn off process, whereas the gate to drain capacitance, it is discharged during the turn on process, it is discharged from that whatever voltage it has from VDC, that is the blocking voltage, and while it is turned off it again gets charged to that voltage of VDC. So, let us write some equations related to these, which will help you in doing some very crude estimation of the requirements of your gate driver. Now, this is just these equations, do not think that they are correct equations, they are linear approximations, and they only provide you crude estimates. Okay, so do not have questions that why it is so, it should not be like this, this is an RC circuit and which these are not really the correct equations, this is not how it should be. You may be having all these questions, but these are all linear approximations, a very crude, very rough way of getting some numerical values which will help you in choosing the gate driver. So, as we had named some of these, so this was your, we named it as IG peak, IG dash PK, and this current is IG dash your PL, the Miller plateau, and over here also this is your interval 2. Okay, this is your interval 1, this is interval 3 which is your Miller plateau period, and then you have another interval which is your interval 4. Okay, so this during this interval, let us say that in between you have this current which is given as IG2. Okay. So, now if we write some equations, very linear equations, so IG2 can be given as your Vg minus of 0.5 VGSPL. Now, this is your VGSPL, okay, plus your voltage VTH, the threshold voltage, by your RG. All right. And why it is so? Because you have this RG over here, gate resistor, then you it is your MOSFET is there, and this voltage, this whatever is our gate to source voltage, during this time this gate to source voltage is equal to your VTH during this interval 2, and here it is equal to VGSPL. So, in between, if we want to find out, that will be half of the sum of this 2. So, VGSPL plus VTH by 2, which is, that is what is multiplied by 0.5. So, that is what you can think the voltage as VGS equal to, and here what you have applied is your capital VG. So, basically the equations that we are writing is Vg minus Vgs by Rg is the current that will be flowing here. So, that is what your Ig2 is taken as equal to. Then next we can write your Ig during the Miller period or Miller plateau region will be Vg minus your Vgs PL by Rg. Alright, this is very straightforward over there. And then during this interval 2, which is your T2 minus T1 in this case as we have named, this will be given as CISS or VGS PL minus of VTH multiplied by Ig2. Now, why we are writing this? Because we know that during interval 2 what is being charged is the input capacitance. So, this is the input capacitance over here which is going to be charged. So, that is your CISS, and so the total charge is the time period multiplied by the current value, and that will be CISS multiplied by this voltage difference, and voltage difference is what? VGS PL minus of your VTH, this week for your interval 2. And then for your interval 3, which is as we have named T3 minus T2, okay, that is equal to your CRSS into VDS off state. Now, here it is equal to VDC Ig dash Miller plateau current Ig dash PL, and we have also written for your peak current of the gate which is Vg by Rg. Okay. Now, these are some of the equations which you can use for calculations related to your gate circuit. Now, one more thing that you have to observe is that this gate current, you can see that this is not a continuous current, it is there during the turn on process and then it is there during the turn off process. In between it is not there. So, that means if we would have drawn this gate current over here, then this gate current Ig would have been something like this. It would have come, you would have observed here, and then this would have during this turn on process and turn off process, we would have seen this gate current Ig. Okay. So, the RMS, if you have to find out the Ig RMS, so that would have been very small value, okay, because there is going to be some loss associated with it, and that loss is your Rg into Ig RMS square, okay, that is the power loss associated with this Rg. And what this whatever is this driver's power requirement, if we call it as P drive, that will be sum of this I square G loss plus I square R loss associated with the resistor plus whatever is the gate requirement, means the power requirement of this MOSFET, which is we can denote it as P gate, and this loss, this is what this P drive, this driver has to supply. So, now what is the P gate equal to? P gate we can find out from this kind of graphs. This we have seen before also when we discussed the devices. This is your gate charge versus your gate to source voltage, and this is similar to this kind of a graph that we see here, the way the voltage is. So, instead of time, this voltage can also be plotted with respect to the charge. So, here it reaches to this threshold voltage. So, somewhere here let us say is your threshold voltage VTH, and then further over here it will reach to your Miller plateau voltage, which we are naming it as VGS-PL. Then after that from here or here, depending on what is the VDS voltage for the MOSFET, the Miller plateau region may change and it may increase. Okay, so, as your VDS increases, so we can see that the how it charges in the further the fourth interval, that is going to, that has got some effect on that. So, this is basically this part is your QGS1, and this part is what is our QGS2, and this part interval in between for the Miller period, this is our QGD. Alright, and the total charge associated with it is equal to your QG, and that depends on how much is the VG that we have applied. So, let us say if 10 volt is equal to VG, so it has to reach to here. So, then your P gate will be written as equal to Vg into Qg into your switching frequency Fs. So, Fs is your switching frequency here, which may be whatever hundreds of kilohertz or 50 kilohertz, 20 kilohertz, whatever switching frequency that you may be using for your circuit. Okay. So, this P gate gives us the estimate of the power required on the gate emitter or the gate source region for the MOSFET or the IGBT. Now, let us look into how do we estimate your what should be the gate resistor that should be used, and what should be the power level of the driver IC. I have already shown you some equations which you can use. Now, let us also see the data sheet which are the specifications which you should be noting down for selecting the, or rather estimating the requirements of the gate driver. This is the data sheet of a power MOSFET of 200 volt and 94 amperes. I have explained this data sheet to you before as well. So, now again revisit it, and let us look into it from the driver perspective. So, from driver point of view, what you see here is that what is given is this gate to source voltage maximum ratings is plus minus 30 volt is what you can apply. Now, further what we see here is the threshold voltage is also given, okay, which is your minimum 3 volt and 5 volt. So, whatever gate to source voltage that you will be applying has to be greater than 3 volts at least. Okay. Then what we see here is this total gate charge is also given. Okay, so, this you can use for your power of gate requirement to do that estimation, the calculation. Then further what we see here is that this rise time TR is also given. Okay. Now, this rise time, how you can use it, we just saw that equation that your this for this Miller time period we can write it as TR, which is equal to your CRSS VDS off by your whatever is the gate current IG dash PL. Although TR is not exactly the Miller period, it is slightly greater than the Miller period, but you either you can use this TR itself what is given in the data sheet, or you can use something lesser than that also. Okay, so from here you can calculate this IGPL, this you can calculate by using this TR value. So, also what you see here is that with these, all these values are given for what they have given, all these specifications. So, VDD is 100 volt, ID is 56 ampere, they already have given some RG value which they have used for this finding out these times experimentally. Now, you may, it is a good value to use these values as the starting point for whatever design you may be doing. You may use it, or you may use something higher than that or lower than that as well, but that gives you first idea that okay, this RG is 1.2 ohms or more than that, or somewhere somewhat less than that, that is what you are going to be using. And what is the VGS voltage? 10 volt, that is also that they have what they have used. So, that also gives you an idea of how much is the VGS you can use to start your experiments with. Of course, 10 volt may be less, you may be wanting to apply more than that, okay, but these are just to give you some starting points to do your design. So, so these are the things that you can note down, and further what you can note down is also your CISS input capacitance and this reverse transfer capacitance values which are also provided, which is what you can use here, and VDS of you know it from your circuit. And plus we have got other equations also that I had shown you, which you can use to do the calculation of your RG. Next, some of the other graphs which are of importance to look into it while designing the or choosing the gate driver circuit is this over here. What you can see here is your drain to source voltage versus drain current, and what is the VGS that is applied. So, you can see here that above around 10 volt or 12 to about 15 volt, it enters into the ohmic region. So, that is a good point to apply like around 12 volts or 15 volts as your gate to source voltage. And then you can also see this transfer characteristics, VGS versus ID. And again what we see here is that your this is the threshold, and then above, as this voltage increases, what is the point when your drain current starts to build up. So, from here also you get an idea of how much is the gate to source voltage that you should be applying. Okay, so you get the idea of your QG, you get the idea of VGS, and some equations are given, I have given you, and plus you also get an idea of RG, what is given in the data sheet. So, from all these different values you get an estimate of what is the gate drive requirement. So, what are the key points of this lecture? So, your gate charge and capacitances, they play very important role in the turn on and turn off process, and so in selecting or doing your choosing your gate driver circuit. And you have to estimate your gate drive requirements, your RG values and other different current and voltage requirement values before being able to choose a proper gate drive circuitry. Thank you.